All right. Okay. All right. Good morning, everybody. This is a great pleasure for me to introduce our speaker today, Dr. Brad Ackerson, who's going to talk us about the latest developments in SARS-CoV-2 vaccine. I met Brad in the early 90s when he was a post-MD and I was a postdoc. And Division of Infectious Diseases and the Department of Pediatrics at HIV-1. This was in the early 90s. And so there was really a lot of things going on at UCLA, especially in the Division of Pediatrics, since that division was the first one to develop a method to treat mothers that were giving birth to kids in order to prevent the transmission of the virus to that mothers. That was a von Reisen. And that was really important, revolutionary. So we were working with Brad in that lab in more basic aspects of virus assembly and budding of HIV-1. I moved on to another lab, and Brad went back to, after he finished his fellowship, he went back to Harbor-UCLA Medical Center. Since then, Brad has been working with many viruses. It really is amazing. You name it, HPV, varicella zoster, hepatitis B, I don't know, there's a whole bunch of viruses that Brad has been working since. He's also a clinical principal investigator in vaccine safety and efficacy at Kaiser. Kaiser is Kaiser Permanente is one of the largest nonprofit healthcare providers in the United States, with over 12 million members. It operates 39 hospitals with 700 medical offices, over 300,000 personnel, including more than 80,000 physicians. And Brad is their principal investigator, vaccine safety and efficacy, member of that, as well as other key positions associated to vaccines evaluation. He has been involved in many clinical trials and has published more than 40 articles in high-impact journals like Vaccine, the Journal American Medical Association, Journal Infectious Disease, Virology, Journal Virology. So, I mean, basically, he's an expert in this area. And so I think that I'm sure you will enjoy his presentation. Also, he's a very good speaker. So go ahead.
Okay, thank you.
One more thing, sorry. The seminar will be in English. The questions will be at the end in English or Spanish. And the ones that cannot do the questions in English, don't be worried. You can say in Spanish and we try to translate them so Brad can understand it. Although he picked up a little bit of Spanish too.
Yeah, I've tried. I tried to take Spanish. I made the mistake of taking French and German through high school and college, which isn't very useful in Southern California, where about half of the people here now speak Spanish. So at any rate, yeah, thank you very much for the introduction. So anyway, the first slide, the title page slide, you can see basically, as Osvaldo said, I'm going to talk about COVID vaccines, a little bit about the history, the development, and the effectiveness. And then finally, we'll touch a little bit on some of the major safety issues. But the first slide is the cumulative incidence of COVID cases, the cumulative incidence rates, I should say, in the Moderna phase 3 COVID-19 vaccine trial. As you can see, the vaccinated group is in red. So the cumulative incidence is almost flat over this roughly 3-month trial versus the placebo group, the control group in blue, which continued to accumulate cases at a pretty fast rate. Now, this had to be absolutely thrilling for the scientists who were involved in this study to see these results when they were finally graphed. It's absolutely outstanding. It's like a home run for vaccinology. The other thing that I like to point out is that, okay, day 0 is when they got the first dose. Day 28 would have been when they got the second dose. You can see on the little graphs, the lines diverge at around day 12. which is phenomenal because that means the first dose already had started to have an impact on their people's risk of infection. And considering that it takes 4 or 5 days to develop symptoms, because these were symptomatic infections, that means the vaccine actually probably started preventing infections somewhere around a week, which is absolutely incredible that a vaccine would work that quickly. Let's see here if I can get this to go. Okay, here we go. So this is the second slide. So this is a brief review. I'm afraid the last year is all too familiar with all of us, but just in a brief review, as you know, early January, we became aware of this new disease. It actually, now we know from blood bank studies where they've gone back and analyzed blood samples, at least in the US and undoubtedly other countries, that there were cases in the US in December. And of course, we know there were a lot of cases in China in December, although they tried to obscure that a bit, I think, for a while. But at any rate, it clearly was in full swing by January, and it spread very quickly throughout the world. It's highly contagious. A Chinese scientist at great personal peril provided the sequence data, and that was published in January of 2020. Essentially, most of the world shut down by March, as we all know, and with a lot of social consequences, including a market rise, at least in the US, of mental illness. I'm sure that was probably true elsewhere too, because of the stresses of unemployment and being locked up and so forth. And but the phase 1 trial results from several of the studies, mRNA, some of the adenoviral and so forth, started to filter in July and really looked very good in terms of immunogenicity. And by November, phase 3 trials results came out, such as the ones I just depicted from Moderna, and really showed that a number of these vaccines worked extremely well, better than certainly my wildest dreams. And then finally, many vaccines were licensed or issued EUAs in the US by December. So vaccination could start in full earnest. So there was light at the end of the tunnel, as they say. Vaccine development requires, first of all, a vaccine concept or a prototype of a vaccine. Then secondly, this all takes time. There animal studies are done that assess the safety and effectiveness, oftentimes non-human primates. And then the human studies are initiated. And generally it starts with phase 1 trials where they try to assess the safety and reactogenicity versus immunogenicity of a number of different dose formulations. The ones with adjuvant, sometimes they try different amounts of the antigen and different amounts of the adjuvant and so forth. So try to work out what is likely to work best. Phase 2 is largely an extension of that in larger populations. And then finally you get to phase 3, which is really where this is the meat of the matter. This makes or breaks vaccines. So you have to be very careful about what you select as your antigen dose and or your dose of adjuvant, because if your vaccine doesn't work well, you're back to the drawing board. And the primary measure here is vaccine effectiveness and also, of course, safety. We'll touch on this a little bit more later. I put the equation here, but it really looks more complicated than it is. But it basically measures the effectiveness of the vaccine, and it's not over a set proportion. Generally, it will be very difficult to get licensure. In the US, this was set by the FDA ahead of any of these results coming out at 50%. So a vaccine to be granted an EUA in the US, FDA announced ahead of time, in spite of pressure from the Trump administration not to do so, that 50% would be the minimum cutoff with a lower confidence interval of 30%. So they wanted to set a reasonable standard for a vaccine. And then finally, you have the post-licensure and post-EUA studies, which is what I'm often involved in. And these are much larger studies once they're licensed. Oftentimes we enroll hundreds of thousands of members who receive the vaccine. They're generally observational, but they reflect the vaccine effectiveness in a real world situation where perhaps refrigeration is not always the best, or the mixing condition is not perfect, or the person administering the vaccine might give it sub-Q instead of IM or whatever. This is real world conditions where things are less than perfect. So we want to see how they behave in these settings also. And we look at larger populations, which in the case of safety studies allows us to look for rare complications, which we're now starting to see with these vaccines. And then we can also look at their performance in subpopulations, which we now know is important even by race. We're now being asked by, for instance, China and Japan and some other Asian countries to evaluate the effectiveness of vaccines in subpopulations within Kaiser that are of Chinese or Japanese or whatever descent. So, and we sometimes see a little bit of differences there as well. So those are all important characteristics to measure. So what was the immunologic basis for the SARS-CoV-2 vaccines? First of all, it started with animal and non-human primate studies that showed that infection with wild type prevented reinfection. And then it was demonstrated that the convalescent serum could be taken from previously infected animals and given to other animals, and that would prevent them from an infectious challenge. And finally, there were epi studies in humans that showed that neutralizing antibody was associated with protection from infection. Therefore, it was surmised that neutralizing antibody should protect against infection from SARS-CoV-2. I think it's important to note, too, that these studies, even though politicians in our news media, I don't know what it's like in Argentina, but in the US, they really tried to make it sound like a miracle, which in a way it was record pace. But this really benefited from studies that had already been done on SARS-CoV, the original 2002 SARS vaccines, as well as MERS vaccines. And so they already knew, for instance, the spike protein was important, spike protein depicted here in this pictorial. In production, that antibody against spike protein was very important in protection. So there was a wide array initially of vaccine types. This is a diagram from a Nature article from April. So this is pretty early, April 2020. As you can see, at that time, there were like roughly 8 different categories of vaccines under consideration. You had viral vectors, both inactivated and weakened viruses, viral vector, replicating, non-replicating, such as the adeno. Adeno was a non-replicating viral vector. Nucleic acid, which initially DNA and mRNA were looked at, and then protein-based, protein subunit and VLP. VLP is used for things like hepatitis B vaccine and HPV vaccine. So these were already, some of these platforms were already in use for other vaccines. So what are our current vaccines? Well, as you know, there's basically 4 different categories that we have. We have the inactivated vaccines coming largely from China, which I understand is being used in Argentina. And this is basically produced very similar to flu vaccine. So they basically grow the virus, they inactivate it, they purify it, and then put it into vials for use. These actually work pretty well. And the second category is adenoviral vector vaccines. And there's 3 basic, right now there's 3 fairly, prominent ones, including the AstraZeneca, which is a chimpanzee adenovirus. The second is Johnson & Johnson, which is the one-shot vaccine. And the final one is the Sputnik, which is also used in Argentina. This one is novel, and I think rather wise idea that they have 2 different vectors, because even though there's very low level virus transcription among vaccinated people, you still can develop antibody and cell-mediated immunity against the vector itself. And if you do that, then you have vector inactivation, and so the second dose might be less effective. And indeed, the Russian vaccine is probably slightly more effective than an AstraZeneca. And you also have the mRNA vaccines. As you know, these were extremely, well, for the most part, successful. Pfizer and Moderna had similar effectiveness. Not surprising, they use exactly the same mRNA construct. The only thing that differs between those slightly is the exact components of the lipid nanoparticle that's used to shuttle that into the cell. CureVac vaccine, as you know or may know, was a flop. CureVac from Germany had some previous experience in production of mRNA vaccines. Nobody really knows why, whether it's the lipid nanoparticle components or it could be the mRNA. They did not use the prefusion configuration stabilized S protein that Pfizer, Moderna, Johnson & Johnson, and Novavax used. So some of these use full length, some used this prefusion stabilized S protein, which is far more immunogenic and seems to have a little less reactogenicity. So it's possible that's why they had a failure. It was less than 50% effective, less than the Chinese vaccine. And finally, the adjuvanted subunit vaccine has just come on the scene. This is produced by Novavax. Novavax has experience. They produced previous vaccines against RSV and influenza that were very successful, the same technology. They produce these nanoparticles of the fusion protein and combine it with a proprietary adjuvant that seems to work extremely well. And their vaccine has similar effectiveness to the mRNA vaccines. So that's pretty exciting. So how do these work? Well, I won't talk about the inactivated ones because those, as you know, they're very similar to flu vaccine. So they're basically just virus that's been inactivated and then purified and injected. Adenoviral vector vaccines, they splice in a gene for the S protein along with its promoter and so forth. And they remove a protein in most cases that's essential for replication. In most cases, they remove the E1 gene. And then the vector itself is grown in a cell line of generally human embryonic kidney cells that are genetically modified to produce the E1 protein so that they can replicate in that cell culture, but not in humans. And then the virus is used to basically shuttle the DNA gene, S gene, into the cell where it produces S protein and leads to the immunity. Those work pretty well. The British one is a modified chimpanzee adenovirus. The reason they did that, they try to choose a vector that has very little exposure in humans, so people won't inactivate the vector, which should theoretically make them more effective. So just a brief history of adenoviral vector vaccines. In the 1950s, in the US, military recruits, so-called military volunteers, and I use the term loosely, were given these live virus adeno vaccines. They seem to work pretty well. And then finally, non-replicating vectors were developed in the 80s, but there was a disastrous treatment. They were largely being used for gene therapy at that time. Disastrous case of a patient in the late 90s was given an adenoviral vectored vaccine gene therapy. And I think portending things to come that we've seen with these vaccines, he died within a couple of days after developing a diffuse thrombotic disorder that looks very similar to the CVST and the pulmonary venous thrombosis that we see in a very small number of adenoviral vector vaccine recipients. However, it's important to note that these, as I mentioned earlier, these were not completely new vaccines. They benefited from previous experience. Janssen had just gotten a Ebola virus vaccine approved in the EU in July of 2020. So this was before they started, getting the results of their COVID vaccine. So there was some experience with this. The Russian vaccine, the Sputnik 5, was approved in Russia in August 2020, but there was some hesitancy and uptake, understandably, and so it was given largely to military personnel initially, and that essentially served as their phase 3 study, which showed it to be very effective. And then AstraZeneca came out later in 2020, and finally Janssen in early 2021. Then we have the mRNA vaccines, and basically this can be either naked mRNA, or in the case of these vaccines, they're actually in lipid nanoparticles that are basically composed of PEG, which polyethylene glycol, which basically determines particle size and keeps them from agglutinating, and cationic lipids, which are proteinized in the endosome so that they can be then released into the cytosol, and also cholesterol to allow them to evade our immune system. And then they had to modify the mRNA in order to make it non-immunogenic. And so the mRNA is basically is essentially injected almost directly into our cytosol, and our cells begin producing spike protein. And as you see, from the vaccine study, the effect is almost immediately seen within days, which I think is absolutely amazing. So the history of mRNA vaccines is much shorter than that for adenoviral vaccines. So they started in the 90s when they showed that you could inject naked mRNA into mice, and in fact, they would produce proteins. And then there were important milestones. Carrico and Weissman showed that you could modify mRNA. It was a uracil they had to modify in order to evade the host defense, because our bodies see this viral mRNA immediately as foreign, and it's highly immunogenic. In fact, there's a vaccine, hepatitis vaccine, that uses a CpG motif as a very effective adjuvant. So that had to be avoided by modifying the uracil. And there were, CureVac actually produced a rabies vaccine that was, and published results in 2017. So these pre-existed this current pandemic. And Graham and the group at NIH and several other collaborators published, or actually patented, the modified fusion protein concept, looking specifically at SARS, MERS, and I forgot what the third one was. But anyway, looking at fusion, might have been RSV, fusion protein vaccine in this pre-fusion stabilized configuration as a possible prototype for pandemic vaccine. So these people had a lot of foresight. But the first LNP product was actually approved 2018 for a genetic disorder. And then finally, as you know, and starting in 2019 to 2020, there were a number of Moderna studies with mRNA vaccines. This also predated the pandemic. They looked at flu, CMV, and Zika virus vaccines. So some of the work had already been done. Now, vaccine effectiveness, you hear a lot about this. It's a very important measure. It tells you how basically effective a vaccine. Efficacy is generally used, the term used, they're the same measure, but efficacy is used to describe the efficacy, basically, of the vaccine before it's licensed. And this comes from randomized placebo-controlled trials. So it's felt to be in some ways, a optimal measure of, it's less subject to bias. When you measure effectiveness, which is the same measure, but done post-licensure, it's done, as I mentioned, in real world conditions where it's difficult to balance, comorbidities. You have to adjust for a lot of things. You try to balance for different possible, things that might impact the measured effectiveness of the vaccine. But it's almost impossible to anticipate everything that could possibly affect that measure, which sometimes explains why you see somewhat varying values of considerably between different studies done in different countries. And that's the reason for that. But it's essentially vaccine effectiveness or efficacy is the attack rate in the unvaccinated group minus the attack rate in the vaccinated group, all divided by the attack rate in the unvaccinated group. So it basically gives you the proportion that are prevented, and it's multiplied by 100 because it's always presented as a percent. But of course, mathematically, that's just simply 1 minus the attack rate in the vaccinated divided by the attack rate in the unvaccinated times 100. So if we take a couple examples just to understand this a little better, if we have a vaccine that prevents all cases, it's an ideal vaccine, then the vaccine effectiveness is going to be 1 minus 0 over whatever the attack rate was in the unvaccinated group times 100, which is 1 minus 0 or 100%. So it's 100% effective. If it prevents half the cases, then it's essentially 1 minus half of whatever the rate is in the unvaccinated, say 3 cases per million, divided by the attack rate in the unvaccinated, that maybe in this case is 6 cases per million times 100 or 50%. Unfortunately, you can also have vaccines that prevent no cases. And in that case, it's 1 minus n over n, which is 1 minus 1, which is 0. And believe it or not, there are actually vaccines that have negative effectiveness. So we found this in a couple of flu vaccines. They actually seem to make disease worse. There was a famous example of that in an RSV vaccine study in the past in children. And actually the vaccinees had a higher death rate than the unvaccinated. So that was a bit of a disaster. So several variables can affect this. It depends on what you look at. So you'll hear some where they look at asymptomatic infection. There's the most common, we look at symptomatic infection. But oftentimes you'll also see vaccine effectiveness measured against severe infection, such as hospitalization, or against death. So all of those can be a little bit different. And as a general rule, vaccines are much better at preventing death or maybe hospitalizations than they are at preventing asymptomatic infection. And that can be a problem because people with asymptomatic and certainly symptomatic infection can be contagious. But it does, what you assess impacts the actual measure. The demographics can affect it, and then comorbidities, the most obvious of which is immunocompromising conditions, but other things can affect it also. Now, there was actually a study from Nature just recently published. It was really interesting. They looked at all these different COVID vaccine studies, and of course, they all use different methodologies. So what they did was they tried to normalize the neutralizing antibody level assay. And the way they did that was they took the level after vaccination and divided it by the convalescent measure in the same study and came up with a ratio. And as you can see, it's a pretty, and then they plotted that again, protective efficacy against this adjusted neutralizing antibody titer. It's actually pretty good, pretty predictive. In the second graph, you can see the predicted efficacy versus the observed efficacy using neutralizing antibody titer, and it's a pretty good measure. So that can be used to assess, to some extent, predicted vaccine effectiveness going forward, which is rather convenient. And here, they depicted this graphically here, which I think is pretty interesting. I had to cut the figure in half for presentation, but the dashed line is basically the convalescent titer, or rather the antibody titer divided by the neutralizing antibody type, the convalescent antibody type, neutralizing antibody titer is equal to 1. So you can see if it's greater than 1 is protective. We know that generally neutralizing titer of at least 20% of convalescent is protective. So they kind of graph this, and you can see that with the mRNA and the Novavax vaccines, they're almost 100% effective. The Russian vaccine is not bad. It's a little bit lower than those. And then you start getting into the other adenoviral vaccines, and they're lower. The Johnson & Johnson 1 dose and the Oxford vaccine is not quite as effective. And then finally you get the Chinese vaccine is roughly 50%, which is about what was seen. And that's, I think, to be expected. That's what you would see in a very good flu vaccine. Now, this is kind of busy, so I basically compared the different vaccine types, very different characteristics. I think the important ones to look at are in red. They're the storage conditions. You look at the Pfizer vaccine, great vaccine, but how many places have -70 freezers for storage of regular pharmaceutical products? We don't even have that in many areas in the US. So that's really not as practical. The other vaccines, most can be stored in the refrigerator or a -20 refrigerators. That's a little more practical. But then you look at price, and the least expensive vaccine, ironically, is the AstraZeneca vaccine. The other one, some of the Chinese vaccines, the pricing seems to be highly political. So you have some countries that are paying as much as the Philippines, for example, paying $38 a dose, and it's suspected that government officials are probably benefiting from that pricing structure. How many doses are optimal? Well, there's different considerations for this. The 1 dose consideration is the type of vaccine. So we know Johnson & Johnson provides pretty good protection after 1 dose. Perhaps prior infection might. We now know that does make a difference. Vaccine shortage. So the UK took a strategy during the shortage of vaccinating as many people with 1 dose as possible. Turns out that was probably a very wise strategy, at least in the short run. It may not turn out to be a good strategy in the long run, because we're now seeing variants resistant to that. Some people are advocating that perhaps children should receive just 1 dose in order to prioritize more doses for adult populations in other parts of the world that are more susceptible. 2-dose considerations is, of course, escape, variant circulation, and emergence that we're seeing. And finally, the 3rd dose and or booster dose we would consider, for instance, with waning immunity, immune compromising conditions, or possible escape variants that are highly resistant to current vaccines. So looking at 1 dose, this is a really nice study from Italy that looked at the antibody among previously infected people who got 1 dose of mRNA vaccine versus previously uninfected people who were given 2 doses. And so if you look at the first figure A is basically just anti-spike IgGs. That's not as useful. You see a wide spread, but they roughly overlap, and the mean is roughly the same. But the more important one is the neutralizing antibody titer. And you can see that previously infected people who received 1 dose actually had much higher neutralizing antibody titer than the uninfected people who received 2 doses. So this suggests that one dose might be very highly effective in these people. And there's now additional data that shows this, but this is the nicest depiction, I thought. Then they looked at, okay, how long should you wait after being infected to get the one dose? And as you can see here, they looked at 1 to 2, 2 to 3, and greater than 3. And at least judging by panel D, which is neutralizing antibody titer, it's probably wise to wait at least 2 months, possibly 3 months. So allowing a little bit longer interval probably provides for better protection. And this is another way of looking. This is similar, except this is 2 doses following infection. And they showed the neutralizing antibody titer a year after infection, plus, in this case, full vaccination, results in very high titers. And so it's protected for at least a year. So vaccination post-infection is very important and provides tremendous protection and likely very high protection against variants, unlike natural infection. So the UK strategy was to give 1 dose, as you know, in order to vaccinate as many people. They figured they could vaccinate twice as many people with 1 dose as they were able to vaccinate with 2 doses. And this was very scientific. This was based on looking at the vaccine effectiveness that they saw with mRNA vaccines, plateaued at 34 days and then was stable. And with adenoviral vaccines, it not only improved through day 35, but it continued to improve after that. So, but unfortunately, they then came along the Delta variant. And the Delta variant, as it turns out, is somewhat resistant to single dose, as well as natural infection-induced immunity. So the Delta variant emergence is really expected. We know that viruses constantly change through mutation, so there's always new variants. And some emerge and some disappear as they're squeezed out. So now we see Delta variant squeezing out a lot of the other variants, because it's crazy contagious. It's 60%, estimated to be 60% more contagious than the Alpha variant, which we used to call the UK variant, the B117. That in turn was 50% more contagious than the original one. So now Delta is roughly twice as contagious as the original Wuhan strains. Important characteristics to consider in these variants is, are they more easily spread from person to person? Delta probably is, because people have much higher viral titers with Delta, and that's what undoubtedly makes it much more contagious. Does it cause milder or more severe disease? There's some suggestion that Delta causes more severe disease in people, and that's probably not too surprising either, because you have much higher viral loads. And then some variants might not be detectable by diagnostic tests. We know that if the mutation occurs in the wrong place, it can lead to non-detection. That was the case of the Alpha variant using the Thermo Fisher test. They may respond less well to therapeutics, and finally, they may affect the effectiveness of vaccines, which we've already seen. So in fact, if we look at Delta versus Alpha, this is the results of a British study looking at, you can see here, any vaccine, 1 dose versus 2 doses, and then they broke it down by vaccine type. It didn't really matter. That it was about, you can see the 1 dose effectiveness against Alpha is about 51%, but it was only 33% against Delta. 2 dose was, protection was maintained. Fortunately, protection against severe disease was still maintained by single dosing. So you can see it's 78 versus 75, so it's not much different. Do we need booster doses? Well, that depends. It depends on the risk of waning of protection or immunity. We now know that's probably less of a problem with mRNA vaccines than possibly adenoviral vaccines. Also, the effectiveness against new variants. We might need variant-specific boosters, and the Moderna and Pfizer, and I'm sure the companies are now looking at this. It also depends on the risk of COVID-19 exposure. If we're lucky enough someday to eliminate COVID, we won't need boosters, but I don't see that happening. It's too contagious and too prevalent and too cagey. This is a very cagey vaccine, virus. It's just continually changing. And then the risk of complications. So there's some people that might, for instance, immunocompromised people or people at very high risk of bad disease might be more, it might be more appropriate to give them a booster than somebody who's unlikely to have a problem if they've already been vaccinated. And then as I already mentioned, the type of vaccine can make a difference. So this, again, this is the same graph from the Nature paper that suggested, again, as I mentioned earlier, that you need a 20% mean convalescent titer to protect against symptomatic disease. But the threshold for severe disease is much lower. It's about 3% convalescent titer. So that's an important consideration. And if this is neutralizing antibody titer after vaccination, you could see it drops. It doesn't drop immediately out through 6 months, but it does decline. So we know that immunity probably declines over time. And in fact, there's another paper from Nature Medicine that noted that the initial vaccine efficacy may help predict the time until boosting is needed. So what they looked at here was the initial efficacy and then a predicted efficacy over time based on neutralizing antibody titer out to 250 days. So you can see that if you have a vaccine, for instance, an mRNA vaccine that has an initial VE of 95%, it would continue to have a VE at 250 days of about 77%. On the other hand, an antiviral vaccine, which typically had about 70% efficacy, would have a lower VE, about 33% after 250 days. So it does appear that boosting may be important. Now, one thing to keep in mind, this assumes that cell-mediated immunity doesn't play a part in long-term immunity, but we know that it does. So it may not be quite that desperate, but nonetheless, there probably is a difference. And this, they presented this another way of presenting it. So here they looked at the time, the efficacy of, say, a 95% versus a 70% vaccine over time, and mild infection versus severe infection. So you can see the severe infection dotted lines, the efficacy remains very high for against severe disease. It drops more against mild infection. And the different numbers basically are based on modeling. So we know that neutralizing antibody titer drops initially exponentially, and then it reaches a slower rate of decay, the 10-year decay rate, in which the half-life is much longer. So how long these are effective depends on how quickly it reaches that plateau rate of decline. So if you reach that plateau rate of decline in 1 year, then you can see that that's the blue line. On the other hand, if it takes 2 years to reach that rate, then that's the red line. That's why the red line's lower. So modeling predicts that boosting may be needed in the long term, but probably not in the short term. And this is another way of looking. This is kind of similar, but they basically, the vaccines with greater VE are likely to have greater VE against variants. So this is really looking against variants. So if you take an example, the variant, typically variants oftentimes have roughly a 5-fold susceptibility, lower susceptibility to the neutralizing titer of when new variants come out. So it would predict to reduce the efficacy from 95% to 77% in vaccines with high VE, or from 70 to 32% with ones with lower VE. So you can see that whether you need a booster is going to depend on what variant's circulating as well as what vaccine you got. And here's some real world estimates of various different vaccines against various different strains. And you can see that the fully vaccinated people have a VE against alpha variant, roughly 85%. It's lower for the gamma, which is not surprising. That was the one we used to call the Brazilian variant. That was, so when you have mixed population, 79%, the gamma, which used to be called the South African variant, it's also lower. And then if you break it down here, that you can see against beta, for instance, in Qatar, Pfizer vaccine was still 75% effective, but the Janssen vaccine had very low effectiveness against the South African variant. So again, the variant versus the disease makes a difference. And this is similar portrayal. This is alpha versus delta. You see these widely varying estimates, but the bottom line is symptomatic infection drops somewhat. They maintain pretty good effectiveness against delta variant, against hospitalization. So it's sort of an extension of the British study, but in a real world populations. Now, immune suppressed persons we now know have poor response. Solid organ transplants are really bad. This was a paper from New England Journal. Basically, it shows that only 50% even respond at all to the vaccine, even if they get mRNA vaccines. And this depicts 30 different studies in immune compromised people. You can see, again, the solid organ transplant are particularly bad, but people on immunosuppressed therapies, people on dialysis, and people with cancer have lower responses as well. So then the question comes up, what about the third dose for these people? And there's pretty good evidence that that provides some benefit. So when they looked at, there's a group at Johns Hopkins, when they looked at solid organ transplants and gave them mRNA, a third dose of a vaccine, not always mRNA vaccine, but they'd already received the mRNA vaccine as the primary series, they found they could get a response in about half of the people that were given a third dose. So these people may require 3 or 4 doses. People on hemodialysis had an upfront seroconversion, about a rate of about 80%. So they weren't as bad as a solid organ transplant. And they could basically rescue about 40% of the people who didn't respond to the first 2 doses. So again, they may need 3 or 4 doses. And then Moderna has an ongoing study that's looking at that. Now, what about interchangeability? So this comes, I get this question a lot. What if I had mRNA vaccine, can I have a different one? Or if I already had the adenoviral vaccine, can I have the mRNA vaccine booster? Turns out that actually works really well. So if this study looked at the first column over on the far left, they got 2 doses of the Oxford vaccine, the AstraZeneca vaccine, and you see the response there, it's 61. For neutralizing antibody titer 50, and then the cellular responses in the lower box is 50. And by comparison, if they got 1 dose of mRNA vaccine and 1 dose following 1 dose of the AstraZeneca, they got a tremendous response. And if you look over in the 2 columns over at the BNT/BNT, which is 2 doses of mRNA vaccine, it basically shows that 1 dose of adenovirus vaccine plus 1 dose of mRNA vaccine gives you a very similar response. And similarly, if you flip them, you get a pretty good response. So if you get 1 dose of mRNA followed by adenoviral vector, you also get a very good response. So that's really very encouraging. Now, what about vaccine safety? You probably heard about the stroke events that occurred with the adenoviral vectored vaccines, but we also know that occurs after coronavirus. And after mRNA vaccines, the primary serious adverse event was the myocarditis seen in young males. So there was a study in the UK where they compared the risk of CVST after the vaccine versus COVID, and they found it was about a 10-fold greater risk following COVID than following vaccine. The only problem is they didn't match for sex and age, which it turns out is very important, because we know if you look at the background epidemiology of CVST, occurs mostly in females, 3 to 1, and the median age is 37, so it mostly occurs in very young people. And in the vaccinated group, it's even lower age group. So they really have to adjust for that. And so when we look then at what's the expected cases versus the cases reported in women after getting vaccine, we know the estimated annual incidences of cerebral venous sinus thrombosis is between 0.5 and 2 cases per 100,000 in the population. So if we look at the number of cases that are expected, they'd be between 0.4 and 1.6. So then when we looked at the number of cases that occurred after vaccination over the same person time, it's between 4 and 15-fold higher than that expected rate. So we know it is higher than the background. It remains to be seen whether it's higher than taking your chances with COVID. And similarly with mRNA vaccine, we know this occurs, unlike the stroke that occurs primarily in young females, this occurs primarily in young males and occurs mostly after the 2nd dose. So if we look here at the incidence rate, after the 2nd dose, it's about 16 per million, which is quite high. And if we break that down by age, it's even greater among young males. So you look at 12 to 29, it's 40.6. And if we break that down further, 12 to 17 is 62. So this is much higher rate in young males. So some people question whether we should give 2 doses to kids, or maybe we should give them a mix and match schedule. So, but I think there's probably ways to optimize the benefit. Perhaps we should give mRNA vaccine to younger females and give adenoviral vectored vaccines to young males, or possibly the mixed schedule, 1 mRNA, 1 adenoviral vaccine, and give the 2nd dose in males as adenoviral vaccine and the 2nd dose in females as mRNA vaccine. So I think there's ways to creative means of decreasing the risk. So the conclusions, there are 4 platforms currently available, or at least widely available. Vaccine effectiveness against symptomatic and severe infection with archival variants is good to really outstanding. But we know that the VE against symptomatic infection with some variants is lower, and it varies by vaccine type. We also know now that 1 dose VE against symptomatic infection with some newer variants is poor, especially the Delta variant and the South African and Brazilian variants. And But the mRNA and antiviral vaccine effectiveness against hospitalization and death by current variants appears to be excellent. And that's probably true of the Novavax vaccine also. Serious side effects have become apparent as the doses. These vaccines now have been given to almost 2 billion people worldwide. So that's what happens when you give vaccines to billions of people. You start to see events that occur in the 1 per million range, whereas we don't see that in the pre-licensure studies. And then finally, as I just mentioned a minute ago, targeting vaccines to optimize protection while minimizing risk may increase vaccine confidence and also reduce adverse events. So that was the main points I wanted to make. I'm happy to field any questions. Oh, got one more slide.
Well, thank you very much, Brad, for your presentations, your interesting presentation. We have some questions. Hernán Pérez.
I think it's really exciting that we have these vaccines and that they were developed so quickly. But I think a lot of the benefit, the incredible rate of development we saw was really because a lot of background work had been done that I think most of the public was completely unaware of. We're fortunate to have scientists like that have the foresight to develop these things.
May I ask a question?
Sure.
I wonder if you have idea of the type of immune response of pregnant women, if it's different from a non-pregnant woman.
That's a good question. That's actually one of the things we're going to look at, or we are looking at in a couple of studies that I'm involved in, looking at Moderna and the Pfizer vaccine effectiveness. And we're looking at pregnant women as a specific subgroup. Pregnant women were allowed in the studies, but they weren't assessed separately because they were pretty small in number. There was a lot of hesitancy, there still is, of women getting vaccinated, even though we know the complication rates in pregnancy of COVID are extremely high. And we've had a number of very bad cases, women that ended up on ventilators, young women who normally would not have had these complications. It's much worse in pregnancy. So that's really an important consideration. It is one we're looking at. But that's one of the advantages of doing these large post-licensure studies that, we'll probably end up with thousands of women that got vaccinated. So we'll be able to compare them with unvaccinated women and look at their rates of protection.
Thank you.
Yeah. There's some suggestion, by the way, that the women that get vaccinated actually passively transfer antibody to their infants. And so it may be somewhat protective against young infants who also have a very high complication rate.
Brad, I have a question. Could you explain a little bit more about the difference between the prefusion construct and the other constructs that it was used? Because I think that is pretty important. I mean, and I am not sure if everybody is aware of that.
Yeah, you're right. That work started with, well, we know that developing antibody against the so-called prefusion configuration is very important because once these viruses adhere to the receptor on the cell, that fusion protein changes configuration to the so-called postfusion configuration. And we also know that these so-called fusion proteins are unstable. So they have a tendency, they're more stable in the postfusion configuration than the prefusion. And it doesn't do any good to develop antibody to the protein once it's already bound to our cells. You really have to have antibody against that protein before it binds to the cell. And so Graham did a lot of work looking at, he actually initially looked at, he was at NIH, looked at RSV vaccines and protection and found that it was much more protective to have antibody against RSV prefusion configuration than post. And in fact, also showed that probably some of the adverse events, the severe bad outcomes that were seen in that pediatric study that I mentioned, were probably because when they formalin and activated RSV, it changed that that fusion protein of RSV to a post-fusion configuration. So it's possible that that having antibody against post-fusion configuration actually may lead to greater reactogenicity and maybe worse disease, as was seen with RSV. And it may also explain the failure of the CureVac mRNA vaccine because they didn't use the prefusion configuration. So what Graham did was they found a way to stabilize spike protein by inserting 2 prolines. And by doing that, it keeps it in the prefusion configuration. And that had 2 major benefits. It increases the neutralizing titer against the prefusion configuration. It also resulted in higher production of prefusion protein by cells that had taken up the mRNA. And the reason for that is the cells that were infected with constructs that did not encode for this stabilized prefusion configuration tend to produce a lot of post-fusion configuration protein. So in order to optimize production of prefusion configuration protein, they found simply inserting those 2 prolines increased the output. They also changed some of the codons to synonymous codons so that it's still encoded for the same amino acid, but they tinkered around with all different combinations and found that by substituting specific codons for other codons, it was still encoded for the same amino acid, but it resulted in much higher production of the spike protein by human cells. So they did try to optimize throughput. Some of the vaccines use that. I think I mentioned Johnson & Johnson, and that may be why it's more immunogenic after 1 dose than the other adenoviral vaccines. The Pfizer, Moderna used it, whereas CureVac didn't, and the CureVac vaccine was not effective enough to market. I should mention also, CureVac should have learned from Pfizer because Pfizer actually used 2 initial constructs. They used one that they ended up marketing, the so-called B2 variant, that was the prefusion stabilized construct, same one that Moderna used, the one developed in NIH. But they also did studies using just full-length spike protein, which is what CureVac used. And they found that the so-called B1 formulation of the vaccine, they found the B1 formulation with the non-stabilized prefusion construct had much higher reactogenicity and less immunogenicity. So I kind of think that CureVac could have probably taken a page out of their book and just gone with the same construct that Pfizer and Moderna used, and chances are they would have had similar results.
Thank you.
Yeah.
Well, we have here in the chat a question from Amparo Assis. Brad, I will read it.
Okay.
Hello, congrats for your talk. There is a paper published in Science by F.A.A.P in 2016 where they report the use of 5 adenovirus in vaccines against HIV. They report that 5 adenovirus increase the risk of contracting HIV. This was not considered in current vaccine. Why do you think this is important? Antecedent was omitted.
I see. So as I understand it, the concern was that having vaccine against adenovirus might increase the risk of HIV, acquiring HIV. Yeah, I'm not familiar with that paper. I'm not sure what the mechanism would be. We know sometimes, for instance, there are studies that show that flu vaccine actually may increase your risk of acquiring other respiratory viruses. And it's thought that it's because by preventing flu infection, you're preventing a priming of the innate immune system. Because flu vaccine is highly motivating to our innate immune system, and the innate immune system, or also called trained immunity, can be more broadly protective. So getting influenza, they think, actually may decrease your risk of getting other respiratory viral infections. And so by taking flu vaccine, you might increase your risk of getting those other respiratory viral infections. Now, of course, in that case, the trade-off is probably worth it because flu is far more serious than other respiratory viral infections. But I could see where perhaps getting an adenoviral infection, which normally is pretty mild, that might, prime your innate immune system and provide broad protection that might also reduce your risk of HIV, might be beneficial. I would wonder, though, also about sort of unanticipated effects of getting a vaccine on human behavior. The British, for instance, found that the risk of getting COVID actually went up for the first 3 or 4 days after getting COVID vaccine, the first dose. And I think what happened was people don't understand the nature of vaccines. They don't understand they take time to kick in. And so I think people went out and hit the pubs thinking, well, I'm getting vaccinated in a couple of days anyway. I'm safe, so I don't have to worry anymore, because it rapidly disappeared. But there's no biological mechanism I can think of that would increase your risk of COVID by getting vaccinated other than human behavior. So, and so I wonder if maybe some of the recipients might have taken risks that they might not have otherwise taken, thinking that they might be getting a vaccine that helped prevent HIV, which was probably the initial goal.
Okay, there is another interesting question of Amparo. Consider that inactivated virus vaccines have more mutations that can trigger the T-cell response, mainly CD8 positive. Do you think it would be more protective against new variants than those that are directed only against spikes protein?
Well, that's a good question. I think really the issue is probably not the type of vaccine, but what type of immunity the vaccine induces. And it is true, vaccines that induce antibody response and cell-mediated response against more conserved portions of the virus are likely to be protective against variants than ones that say direct the response against less conserved. So I think it is possible to have a spike protein vaccine that induces response against portions of the spike protein that are conserved that would be more broadly protective. And there's an example of this in the Novavax flu vaccine. Novavax produced what turned out to be a highly effective flu vaccine using the same technology they're using to produce their COVID vaccine. And what was found, though, was they used an adjuvant that induces a very good immune response and actually made it a little more broadly protective than normal flu vaccine. It was actually protective against unrelated strains of flu that emerged during that flu season. So they did some assessment of what antibody it might induce, and they looked at the stem part of the HA protein, which is like a fusion protein, and against vestigial esterase, which is part of the head of the HA protein. And they found that, in fact, it induced very high titers of antibody and cell-mediated immunity against those highly conserved parts of the influenza HA protein. So I agree. I think there are some vaccine platforms that by their very nature may induce more broad protection. I think the mRNA vaccines do, because they're highly immunogenic. And I think that's part of the reason. And mRNA and adenoviral vectored vaccines are considered autoadjuvanted. And so they're really like getting a vaccine with a very strong adjuvant, and which is similar to the Novavax vaccine that induces a very strong immune response. And it's probably a broader response, similar to what they demonstrated with their flu vaccine. So the Chinese vaccine is not particularly protective against some of the newer variants. It is against severe outcomes. So it's still very effective against hospitalization and death. But it's not as protective against symptomatic infection. And it's a little concerning because in general, people who get symptomatic infection could be contagious. So it's about 35% protective against symptomatic infection by the Delta variant, for instance. And so you worry about the 2/3 that still get symptomatic infection, how contagious they are. They're probably less contagious than unvaccinated people, because I would bet that their viral load is lower than unvaccinated people. So I think it still provides some, population benefit as well.
Well, thank you. I read another question of Hernan Perez. Hello, everyone. I would like to thank you for the seminar and ask how reliable the antibody titer is to measure the effectiveness of vaccine, and if you think it is important for this study to monitor the memory level of T lymphocytes. Perhaps this type of analysis will allow us to know with greater certainty if more doses will be needed in the future. Thanks.
Yeah, sure. No, I agree. And I think that was a caveat of that one Nature study, that I think it's highly predictive of early response and neutralizing titer early on and likely early effectiveness. But I think that the efficacy and effectiveness long-term are not as easily measured by just neutralizing antibody titer. I think it is probably somewhat predictive, but not completely. That's actually the purpose of our studies is really that I'm involved with Moderna and the Pfizer studies that we're doing here at Kaiser is long-term effectiveness. And we're actually going to be looking at 3 years effectiveness for the Pfizer study and 5-year for Moderna. So that should give us, that's a long, and this is actual measure of how well do they really work, and how well do they work at 6 months, 1 year, 2 year, 3 year, 4 year, and so forth. And I think that's really the ultimate measure of when boosters might be needed and in which populations it might be needed. I think we already know they're going to be needed almost for certain immune compromised people. Other populations, it's probably going to depend somewhat on the population comorbidities and so age and so forth.
Okay. Eloisa Arana, you have a question. I'm not ignoring to you.
Yeah.
The problem that's I am a bit nervous because my English is not so good.
Okay.
Go ahead. Go
Probably
ahead.
better than my Spanish. So.
So great presentation, Brad. Thank you very much. So of course, we are more interested in the vaccines that are being used here in Argentina for certain reasons. So as you asked before starting, and Osvaldo told you, most of the vaccines used here are viral vector-based vaccines, and there is the Sinopharm from China, but I think most of the population got Sputnik or AstraZeneca, which, as far as I understand, they use the wild-type version of Spike. This is what is expressed in both of them. The vector is different. So, as also Osvaldo said, we had problems in getting the second dose of the Sputnik vaccine. So there was this discussion over here about mixing both viral vaccines, which I thought that last year in the UK, they did some, I thought in my mind that they did an experiment mixing also the AstraZeneca with, I don't know which dose of Sputnik, but I haven't seen the publication. Now that there are small studies that started here, like in an emergence to try with few people to mix both vaccines. From the theory, as far as I can see, there wouldn't be much of a problem, but what do you think that are more?
Yeah. No, I think, well, yeah, I absolutely think that it'll work fine. And the reason for that is they're all basically directed against spike protein. So there are some vaccines, for instance, that you can't mix. The meninge B vaccine, for instance. So Bexsero and Trumimba actually are directed against different proteins. So you can't get one dose of one and expect to get a boost response from the other one because they're directed against 2 different proteins. In this case, they're really directed against exactly the same protein. And which is why I said, I think if nothing else, you could just get a second dose of the first dose of the Russian vaccine because they're the same construct. It's just one's adeno 26 and one's adeno 5, which in all honesty, I think was really a smart idea. It turns out vector inactivation is probably less of a problem than I thought it might be for the AstraZeneca vaccine, but I thought the Russians were really onto something, and that may explain why their vaccine is slightly more effective than AstraZeneca. It could be that made a small difference. I think I'd really be worried down the line about booster doses using the same, viral construct. So it's likely, in fact, using the Russian and one dose Russian, one dose of the AstraZeneca, I think is an interesting idea because one is adeno 26 and the other one's a chimpanzee adeno. So they're also going to be completely unrelated. But I think the British study that showed mix and matching AstraZeneca with Pfizer demonstrates this concept works really well. I think, personally, I think the ideal would be to get one dose of adeno, one dose of mRNA vaccine. We don't know long-term, but just based on the short-term immunogenicity, it looks like it'll actually be very good. And you might be able to optimize protection and minimize adverse events, particularly among young people.
Okay. Amparo Assis had the last question. He or she promised. Having vaccines made with recombinant protein or inactivated virus, which are better now technology in relation to their long-term effects than the new ones with RNA or DNA, which were also developed in record time. Do you consider that it would be safer to vaccine adolescents and children with this type of vaccines?
Yeah, I think that's a great question. I actually agree. I think that, in fact, in all honesty, I think Novavax is largely positioning themselves as a booster dose because they know that much of the market is becoming more saturated with, especially the lucrative market, is saturated with existing vaccines. So there's already adenoviral vaccine, mRNA vaccine. Most people are going to get vaccinated in lucrative markets, have already been vaccinated. So I think what they're really positioning themselves for is a booster dose. And I actually think that would be certainly an excellent concept in kids. I would personally go with the Novavax vaccine over the Chinese vaccine, or maybe one dose Chinese, one dose Novavax, simply because it has almost twice the effectiveness of the Chinese vaccine up front. So I think that future boosts will probably be less important. Novavax vaccine is based on technology that they developed over the last little more than a decade, and they have used in very large populations, including pregnant women, in the form of their RSV vaccine, and was found to be very safe and highly effective. And then, as I mentioned, their flu vaccine is also highly effective, and at least the initial data suggests that it's highly effective against COVID. So I agree. I think that would really be a prime candidate for kids. I'm really worried because when you look at that 12 to 17-year-old, their incidence rate of the myocarditis is much higher than it is in the even 18 to 29. So you worry about what's going to happen in the, say, 6 to 11 or the 2 to 6 or whatever. Now, that said, we don't know the long-term significance of the myocarditis because most of those kids recover within a day or two. I've seen a couple, well, not personally seen, but I've been consulted on a couple of cases. So it's by no means rare. And we have to weigh that against the risk of cardiac involvement with COVID infection, because we know from some studies in which returning college athletes who had COVID, even if all they had was a positive nasal swab, had to undergo cardiac testing. And we know that there's several studies now that demonstrate that between 0.5% and 3% of those returning college athletes have evidence of having had some cardiac involvement. We don't know what extent it was, but I think it's significant that they have residual findings on cardiac MRI or other testing, echo, that suggests that they had some probably some cardiac involvement. And again, we don't know the long-term consequence, but that's a much higher risk, at least rate-wise, than the myocarditis that we see after vaccination. But I agree, avoiding those in kids may be something we have to look at down the line.
Well, thank you very much.
Ariel, I have one more question.
Okay.
Me
Can I
too.
go? All right. I have one question that has to do with something that we discussed several times with Brad, and it's the fact that the known clearance of the virus in the body and how this affect the emergency of new variants. Can
Right.
you say something about that?
Yeah, that's been an interesting finding. So initially they knew an immune compromised people can be chronically infected with COVID. They don't clear it. And so they tried treating these people with monoclonal antibody, and all they did was basically result in emergence of strains that were resistant to the previous monoclonal antibody. And now they use double combinations, but now we know that the virus can even become resistant to those. And so that certainly occurs naturally in people who are not immune compromised who become infected, because we know that you can excrete virus for up to a week or 10 days or so, and a few days prior to becoming symptomatic, and for up to a few days after becoming symptomatic, and that during that time the variants, just through natural viral replication and mutation and so forth, we just randomly produce various different variants. And the ones we produce that infect other people are going to be whatever that person is not immune to. So it's basically that, it drives new variants just through population dynamics and viral mutation. So, and we know that with some of the newer variants, for instance, Delta variant, people have much higher viral loads, and they had them for longer periods of time. So I think it's no accident that many of these variants, such as the Alpha variant, appear to have been the backbone for development of subsequent so-called escape variants that escape from current naturally acquired antibody, or antibody acquired through single dose or suboptimal immunity from single dose vaccination.
Thank you.
Yeah.
Well,
Eloisa, you have another question, please.
Yes, the last one, poor Brad. Thank
Okay.
you for all the time you're dedicating to us. This is the last one, I promise.
Sure.
Regarding long COVID and vaccination, because I've read in Argentina, I don't think this is a big problem, or at least it's not so much reported, I guess because the first wave was not as important as in the US or the UK. But I've read that in the US, people with long COVID have improved with vaccination. Are you aware of this? Do you know anything about this? Just in case after our second wave, which has been much more important, this could be a solution. I don't know, getting more doses of vaccine.
Yeah, that's a great question. And you're right. There have been a large number of anecdotal reports that people improved after vaccination who had long-term symptoms from COVID. I suspect that may depend somewhat on the type of symptoms they have and what those symptoms resulted from. So for instance, people with so-called foggy brain, we know that probably results from microthrombosis because of past studies that show that people who died from primary pulmonary COVID have nonetheless evidence of diffuse anoxic brain damage from this microthrombosis that occurred in the small arteries. So those people might not benefit, but people who have just other more general symptoms like fatigue and things like that might well improve. But you're right, there has been some suggestions, some people improved. I think there have been a small number of cases where people worsened, so it might be a little bit of a gamble, but it's probably one worth taking.
Well, thank you very much again, Brad. Osvaldo, if you want to close the seminar, please.
okay. Well, Brad, thank you. I think that everybody enjoyed your seminar, and you brought a lot of information. Some of the information we were aware, a lot of them we were not. And I think that it's good to know a little more about this vaccine and these things that are going on. So really, we appreciate your time and dedication. I hope maybe in the future you can give another seminar with some update or how things are going, let's say in a year or something like that.
Yeah.
Particularly taking into consideration these long-term studies that you are carrying on with these two vaccines. And I think that it's going to be a lot more of information in the future. And since there's a large interest in our institute in immunology, I think that people will benefit from knowing a little bit more about the evolution of these diseases and how affect the immune system and the responses. And so we are really grateful for your seminar. Thank you very
Well,
much.
thank you. No, I'm glad. I hope it was interesting and helpful. And you're right. It's like an evolving field. It's just, I'm glad I started early keeping folders of articles on COVID because it's really hard to keep up now.
Well,
Keeps it
thank you.
interesting.
Goodbye. Bye-bye. Thanks again.
Thank you.
Bye-bye now.
Thank you.
Bye-bye.
Thank you.
Bye.
Bye.